Hi everyone, welcome to Go Classes. So let's discuss the solutions of today's DPP. Let's start the session. Before we start, please let me know audio, video, volume, echo. Is everything fine? Everything is clear? Let me know. Hi all, welcome to Go Classes YouTube DPP series for GATE CS, the GOAT DPP series. And today's DPP, that is subject digital logic, and the topic is K-map with don't cares. All the questions are taken from MIT. The GOAT DPP series, the complete playlist link you can find the link you can find in the description, also in the pinned comment. Basically, we have started Go Classes YouTube DPP series for GATE CS, where you will be getting top quality questions from the standard resources. All these questions will be within the GATE CS syllabus. Also, their level also will be within the GATE CS level. Okay. So on YouTube, you can search GATE CS DPP, and then this Go Classes YouTube DPP lectures will be shown to you. So here you can notice one thing here. Look at this Gate CS GOAT DPP series playlist link. So here you can find the playlist link. Okay, you can check out the playlist for all the days. You can see this is a video from day 3, and you can see right now we are discussing day 4. Okay, today's DPP, that is basically day 4. Okay. So today, let's solve this question. A K-map is given to you. Here, remember, these are basically 4 copies of the same K-map. Okay, so just ignore the remaining 3 copies, because here you can see the figure 1 shows 4 copies of the same K-map. Okay, so just focus on one of the copy, or I can say on this K-map you focus. Then based on this K-map, there are total 5 questions. You can see question 1, 2, 3, 4, 5. Now, one more variation from Go classes side I have provided to you. So you can see this is Go classes variation of the previous MIT question. Here I am just changing the function. Now you can see all these 5 questions you have to solve for this given function with don't cares. Okay. So very simple. Now let's solve. First we are going to solve the original MIT question. You can see this K-map is given to us with don't cares. Here you can see there are 3 don't cares. So we already know that a function with don't cares, it represents a class, a set of functions, right? Every don't care, it can be either 0 or 1. Each don't care has 2 choices. It can be 0 or 1. So I can say that this function, this is incompletely specified function because it has 3 don't cares. So we call it incompletely specified function. This is not completely specified function because there are don't cares. Now, a function with 3 don't cares will represent a class of 8 boolean functions, because remember every don't care can be either 0 or 1. So you can see every don't care has two possibilities, two choices. So I can say this incompletely specified function, this actually this corresponds to a set of a class of 8 functions. Okay. Now let's see the part 1. The part 1 is show the groupings that correspond with minimal product of sum for this function. So basically, for this function, for this K-map, we need to find the minimal product of some expression. Let's call it MPS, minimal product of some expression. The question is asking the grouping also, and in the second part, it is asking the expression, the minimal product of some expression. And the third part is it is asking the grouping for minimal sum of product expression, and in the part 4, it is asking the expression for minimal sum of product. And the question 5 is interesting. It is asking that in the part 1 and 2, the minimal product of some expression that you are getting, and in part 3 and 4, the minimal sum of product expression that you are getting. So are they logically equivalent? In part 1, 2, we are getting minimal product of some expression. In part 3, 4, we are getting minimal sum of product expression. So these expressions, or I can say these functions, are they logically equivalent or not? This is our fifth equation. Okay, so let's solve it. First we are going to find the minimal product of some expression. Means first we are going to solve the part 1 and 2, then we will solve part 3 and 4, then we will see, then we will compare, and we will see part 5. Okay, so let's see it here. First let's focus on minimal product of sum. Okay, or as MIT is calling it MPS, minimal product of some expression. Okay, so to find the minimal product of some expression, we are going to cover all the zero cells. We will cover all the zero cells with minimum number of cubes, every cube as large as possible. Also remember, if some don't care is useful, we can use it. If some don't care is not useful, we will not use it. Basically we don't care about the don't care. We only need to cover the zero cells. Here you can see in this K map how many zero cells are there. There is only one zero cell is there. So to find the minimal product of some expression, we will cover this zero cell with minimum number of cubes, every cube as large as possible. So here, will I make this type of cube? This cube will I make? No. Here what I can do, I can use this don't care, and this cube I can make. Notice, can I make 4 size cube? Here you can see that we cannot make 4 size cube because here there is one cell. We need to cover all the zero cells. We cannot cover any one cell. Don't cares we may or may not cover. If it is helping us get a bigger cube, then we can use don't care. If it is not helping us in getting a bigger cube, then we will not use it. Okay, so here you can see that this 2 size cube, this is the maximum size cube I can create covering zero cell. Okay, yes or no? So that's it, very simple. Now let's write the, this is the grouping. Remember, this is the part 1. You can see the part 1 is asking the grouping that will correspond to minimal product of some expression. So this is the answer for part 1, means this grouping is the answer for part 1. Now let's see the part 2. Part 2 is asking the expression, the minimal product of some expression. So for that, what we will do, let's label the areas in this K map. Here you can see on the column we have variable AB, on the row we have variable C. So here let's label the areas in this K map because we are finding the minimal product of some expression. So this is the area A bar. You can see this is the area B bar. And you can see this is the area C bar. Very simple. Now here tell me what is the sum term, because remember we are finding the minimum product of some expression. So for this cube covering zero cells, for this cube we will write sum term. So what is the corresponding sum term for this pink cube? So you can see this cube, this is in the area A, because remember this is the area A bar, so this is the area A. So this is in the area A, also this is in the area C. So I can say that A or C, because we are writing the sum term, so A or C, that's it. So finally your answer will be what? So I can say that minimal product of some expression that we will get, that will be A or C. This is the answer. Okay, very simple. Now we have solved the part 1 and 2. Let's solve part 3 and 4. Let's find the grouping for minimal sum of product, and let's find the expression for minimal sum of product. Okay, so now minimal sum of product expression we need to find, or the MIT is calling it minimal sum of product MSP. Okay, so let's see what will be the grouping. To find minimal sum of product expression, we will cover all the one cells with minimum number of cubes, every cube as large as possible. Correct? Okay, so let's see it here. These are the one cells. We need to cover all these one cells. We cannot cover any zero cell, and these one cells we will cover with minimum number of cubes, every cube as large as possible. So tell me, can I make 8 size cube? No, I cannot make 8 size cube. If I make 8 size cube, then this zero cell we are covering, which we cannot do. So maximum 4 size cube I can create. Can I make a 4 size cube? Yes. You can notice this 4 size cube I can make. This 4 size grouping I can make. Now you can notice these 3 ones we have covered, but still this one is remaining. So to cover this one, what is the largest cube possible? You can see that this is the largest cube possible. This 4 size cube I can make. Correct? Okay, very simple. Now you can see we have covered all the one cells with minimum number of cubes, every cube as large as possible. So now we can write the minimum minimal sum of product expression. Remember, minimum sum of product or minimal sum of product, both are basically the same thing. Okay, so let's see. First, you label the areas in this K map. So you can see that because you are finding the minimal sum of product expression, so you can see the area where variable a is 1, that will be area A. The area where variable b is 1, that will be area B. And the area where variable c is 1, that will be area C. Okay, now this grouping we have done. So we have answered the third question, grouping for minimal sum of product expression, that we have done. Now let's write the minimal sum of product expression. Okay, so for that, what we will do, for these groupings we will write the corresponding product term. Okay, for minimal sum of product we will write the product term for these cubes. So you can see this cube, this pink cube, this is in the area A, so the product term will be A, that's it. Next, you can see this blue cube, this is in the area C, so you can see the product term will be C. So finally, the minimal sum of product expression that we got, that is basically these product terms we got. Now we will do their or. Okay, so we will do their or. So we got A or C. Okay, very simple. Now notice one thing, that the minimal sum of product expression that we got, that is A or C, and the minimal product of some expression that you got, that is also A or C. So remember, for this K map, or I can say for this incompletely specified function, the minimal sum of product expression that you got, that is A or C. The minimal product of some expression we got, that is also A or C. Now look at the fifth question by this MIT. So you can see fifth question is, are these functions logically equivalent? This minimal product of sum and the minimal sum of product expression that you got for this K map with don't cares, then are they equivalent? So here you can see, yes, they are equivalent. They are logically equivalent. Both are A or C, so they are logically equivalent. They are logically equivalent. So you can see that for this K map, or I can say for this function with don't cares, the minimal sum of product and minimal product of sum, both the expressions are logically equivalent. Okay, this is the answer. Very simple. Now my question is it necessary that if you have a function with don't cares, for that if you write the minimal sum of product and minimal product of sum, then will they be always logically equivalent? Is it necessary that for a function with don't cares, minimal sum of product and minimal product of sum, these expressions, will they be logically equivalent always? The answer is no. They may or may not be logically equivalent. And for that, I have given you this go classes variation. So you can see this is the go classes variation for the previous MIT question. This function you consider, this is a function with don't cares. For this function, you solve all these 5 parts. And then one thing you will notice, that for this function with don't cares, the minimal SOP expression and the minimal POS expression, they will not be logically equivalent. That is the beauty of this go classes variation that I provided to you. Basically, this beautiful point somehow got missed in this MIT question. Yes or no? Because in this MIT question, for this function with don't cares, the minimal product of some expression and the minimal sum of product expression, they are basically logically equivalent. Okay, but it is not necessary that for a function with don't cares, the minimal SOP and the minimal POS will be logically equivalent. It is not necessary. They may or may not be. Okay, so let's solve the go classes variation for the previous MIT question. We have this function over 3 variables ABC. Here you can see we have this don't care combination also. So let's first let's draw the K map. Okay, let me put variable AB on the column, variable C on the row. Okay, so you can see this is standard numbering 0 0 0 1 1 1 1 0 0 1. Okay, very simple. Now let's find the minimal product of some expression. Okay, minimal product of some expression. Okay, so for that, what we will do, we will fill this K map with 0 cells and don't cares. Correct. Notice one thing, that these are the min terms, means for these input combinations the function value is 1. So where the function value is 0, so you can see the function value is 0 here, the function value is 0 here, because you can see this is the numbering 0 1, then 2 3, then 4 5, then 6 7, right? Correct. Okay, so you can see the function value is 0 here, 0 1, then 2, here the function value is actually 1. Okay, next, so 0 1 2 3, then 4, here the function value is don't care, then 5, here the function value is 0, then 6, here the function value is 1, and then 7, here the function value is 0. Okay, is this clear? So you can see we have filled the k map now, very simple. Okay, you can see this is the numbering, you can see 0 1 2 3 4 5 6 7. Okay, so very simple. Now let's find the minimal product of some expression. So to find the minimal product of some expression, let's label the areas in this k map. You can see the area where variable a is 1, that will be now a bar, because we are finding minimal product of some expression. Okay, so here you can see the area where variable b is 1, that will be b bar area. The area where variable c is 1, that will be c bar area. Okay, now to find the minimal product of some expression, we will cover all the zero cells with minimum number of cubes, every cube as large as possible. Correct. Okay, so here you can see what I can do. Notice one thing, this 4 size cube I can create. Notice that to cover all the zero cells with minimum number of cubes, every cube as large as possible, this 4 size cube I can create. You can see this 4 size cube is creating, this 4 size cube is basically covering zeros or don't care. We cannot cover any one cell, but yes, don't cares. We don't care about don't care. So we may or may not cover. Here it is useful because we are getting a 4 size cube. So we are covering it. Okay. Means basically we are treating this don't care as a zero. Okay. We are considering this don't care like a zero. Very simple. Okay. Are you getting my point? I am saying that for this, to find minimal product of sum, we will cover all the zero cells with cubes as large as possible and minimum number of cubes. Now here you can see, because with the help of this don't care, we are able to get, 4 size cube. So that is the reason we are covering this don't care. It simply means that this don't care we are treating like zero, means we are assuming that this don't care is zero. Okay, every don't care has two choices, it can be zero or it can be one. We can consider any don't care according to our choice, according to our desire. So here I'm considering this don't care like a zero, that okay, this is zero. So very simple. Now you can see this cube I got. Now did we cover all the zero cells? No. Here you can see that these two zero cells are still remaining. So let's focus on this zero cell. From this zero cell point of view, you can see this is a useless neighbor because this is one cell. This is a useless neighbor. These are one cells. You can see this is a useful neighbor. So with help of useful neighbor, this cube we will create. Let's focus on this zero cell. From this zero cell point of view also, these are the two useless neighbors. So there is only one useful neighbor, this. Okay, so with help of useful neighbor, this cube we will create. So now we have covered all the zero cells with minimum number of cubes, every cube as large as possible. Correct? Okay. Now let's write the minimal product of some expression. So for each cube, we will write the sum term. So you can see for this yellow cube, what is the corresponding sum term? This yellow cube, this is in the area B. Okay, you can see this is the area B bar. So automatically this yellow cube, this is in the area B. Next, you can see for this pink cube, what will be the corresponding sum term? This pink cube, this is in the area A, this is in the area C. So the sum term will be A or C. What about this white cube? This is in the area A bar, this is in the area C bar. Okay. So the minimal product of some expression that we got. Now we will do the product of these sum terms. Okay. So you can see A or C, A bar or C bar. I hope you understood. Okay. So this is what we got. Now just notice one thing. This minimum product of some expression that you got here, to get this expression, basically what we considered this don't care, we considered it 0, right? Yes or no? Basically, if you make the K map, notice, if you make the K map for this minimum product of some expression that you got, A, B, C, then the K map that you will get, it will be like this: 0, 0, 0, 1. Basically, everything will be as it is. You can see 0, 0, 0, 1, 1, 0. This don't care, we are considering as 0. Correct? Okay, so let me write that we are treating as 0. I hope you understood. So remember, very simple point. This is the K-map we don't care. Now, from this K-map, or I can say for this function we don't care, we are finding the minimal product of some expression that we have found. But I'm just saying that to get this minimal product of some expression, we are basically treating, we are considering this don't care as a 0. Okay? Or I can say that from this minimal product of some expression, if you draw the K-map, then this is the K-map that you will get. Okay? Now let's find the minimal sum of product expression. Okay. Now let's find minimal sum of product expression from this K-map, or I can say for this function we don't care. So let's find the minimal SOP expression. To find the minimal SOP expression, we will cover all the one cells with minimum number of cubes, and every cube as large as possible. Here you can see these are the one cells. I need to cover them. So tell me, these two one cells I need to cover with cubes as large as possible and minimum number of cubes. Focus on this one. From this one point of view, you can see all the neighbors are actually useless because all the neighbors are zero cells. So all the neighbors are useless. So I can say this cube I will get. Next, you can see from this one point of view, you can see this is a useless neighbor because these are zero cells. There is one useful neighbor. So I will make cube like this. Okay, correct. Now notice one thing, that when you make this cube, it simply means that you are considering this don't care like a 1. Yes or no? You are considering this don't care like a 1. So very simple. Now let's label the areas in this K map, because we are finding minimal sum of product expression, minimal SOP. So the area where a variable is 1, we will write that variable directly. So you can see this is the area A, this is the area B, and you can see this is the area C. So for these cubes, we will write the corresponding product term. Okay, so you can see what is the product term for this yellow cube. This is in the area A bar, this is in the area B, this is in the area C, A bar B C. For this white cube, what is the corresponding product term? So you can see this is in the area A, this is in the area C bar. Very simple. Now you can see the minimum SOP expression that we got. You just do the sum of these product terms. So I can say AC bar or A bar BC. Okay, this is what we got. Now notice one thing, that to get this minimal SOP, to get this minimal sum of product expression, basically this don't care you are considering like a 1. Yes or no? We are considering this don't care like a 1. That is the reason we are making this cube. So from this minimal SOP expression, if you draw the K map, you can check it out. If you draw the K map, then what will happen? Everything will be same, but this don't care we are considering like a 1. So you can see everything else that is same, everything else is same, but this don't care we are considering, we are treating like a 1. Okay, so I hope you understood. Now what is our question? Our question is that for this function we don't cares, you find minimal product of sum, you find minimal sum of product, and then you check these two, means minimal POS, minimal SOP, are they logically equivalent? This is the question. This is the fifth part. Are they logically equivalent? Now you can see here they are not logically equivalent, because notice, for minimal SOP, this is the function we don't cares. To get minimal SOP, we are considering this don't care like a 1. And to get minimal POS for the same function, to get minimal POS, this don't care we are considering like a 0. So notice this minimal POS that we got, this minimal POS expression that we got, this corresponds to this K map. And you can see this minimal SOP expression that we got, this corresponds to this K map. And they are definitely not logically equivalent, because here you can see this is 1 and here this is 0. So they are definitely not logically equivalent. Yes or no? I hope you understood. So finally, here you can see the answer will be what? Are they logically equivalent? The answer is no. Okay. So let me just tell you the conclusion. You can see here, if you see the minimal SOP for this function, if you see the minimal SOP we found that is AC bar or A bar BC. AC bar or A bar BC. This is the minimal SOP we got. Okay. And for this minimal SOP, you can see AC bar or A bar BC. For this minimal SOP, if you see the K map, the K map will be, you can see 0 0 0 1 1 0, and here you can see there is 1. Correct? Okay. Now let's see for the same function. Let's see what is the minimal POS. Minimal POS we got B into A or C and A bar or C bar. Okay. So this is the minimal POS, and for this minimal POS, if you draw the K map, that will be different from this K map, and the difference will be in the position of don't care. So you can see everything else is same, but you can see here this will be 0. Okay. So very easily you can see that these expressions are not logically equivalent, right? Yes or no? So I can say, so for this given f, for this given f, for this given f, here for this given f we don't cares, because this is a function. For this given f we don't cares, because this is a function we don't cares, right? So for this given f we don't cares, you can see that the minimal SOP for f is not logically equivalent to minimal POS for f. Okay. I hope you understood. So you can check this expression, they are not logically equivalent. You can easily check. You can consider when AB is 1 0 and C is 0. Okay, so let me just show you that. Look at these expressions. We got this expression, right? This minimal SOP expression that we got, that is, AC bar or A bar BC. And this minimal POS expression that we got, you can see that is B, A or C, A bar or C bar. Correct? Okay. So here you can just quickly see that they are not logically equivalent. The reason, you can just put, for example, let's put A1, B0, C0. Let's put. So here, what this expression will become? They are not logically equivalent, right? Okay. You can see they are not logically equivalent. Here, just put this. Then here, what this minimal SOP will become? This minimal SOP expression. If I put B0, C0, then it will be 0. And A1, C0, so it will be 1. And you can see what this minimal POS expression will become. If I put B0, then this whole thing will become 0. So definitely you can see that they are not equivalent. Yes or no? Very simple. I hope you understood. So that's it. So finally, I just want to tell you one thing, that if you have a function with don't cares, then for that function, the minimal SOP and the minimal POS, they may or may not be logically equivalent. The reason is very simple, because a function with don't cares, that corresponds to a set of functions, a class of functions. In our Go class lectures also we have seen this, that a function with k don't care combinations represents or corresponds to a set of 2 power k distinct functions. Because remember, every don't care can be either 0 or 1. Every don't care has two choices, two possibilities. So you can see if you have a function with k don't care combinations, then it will correspond to 2 power k distinct functions. You can see since each don't care can be specified as either 0 or 1, so a function with k don't care corresponds to a class of 2 power k distinct functions. Okay, and this is the note. You can see for a boolean function f with don't cares, the minimal SOP for f and the minimal POS for f need not be logically equivalent. May or may not be. May or may not be. So they need not be logically equivalent. They may be logically equivalent, they may not be logically equivalent. But remember, if you have a fully specified Boolean function, means a function without any don't cares, then definitely, obviously, the minimal SOP, minimal POS will be logically equivalent. Because if you have a function without don't cares, then the minimal SOP, minimal POS, these are just two different expressions for the same function, so they will be logically equivalent. But if you have a Boolean function with don't cares, then minimal SOP for f, minimal POS for f may or may not be logically equivalent. Okay, I hope you understood. So let me just give you the conclusion here. If you have a function with k don't cares, then you can see, let's assume you have this function f, and this function f has total k don't care combinations, means there are total k input combinations for which the function output does not matter. Okay, let's assume this is a function over these variables a1, a2, and so on, an. Okay, so there will be total how many rows? There will be total 2 power n rows. In the truth table there will be total 2 power n rows, means there are total 2 power n input combinations, and for k of these combinations, the function value f we don't care. Okay, so you can see there are total k don't cares. This function has total k don't care combinations. So let's assume it's like, there is a don't care combination, then there is another don't care combination, and so on. Okay, and so on. Total k don't care combinations are there. Correct? Means there are k input combinations for which the function output does not matter. Okay, very simple. So now you can see this function, this is incompletely specified function. Okay, this type of function f, this is called incompletely specified function. Incompletely specified function. Okay, now this type of function which has k don't cares, this corresponds to 2 power k distinct functions. Okay, so here you can see that this function f actually corresponds to 2 power k distinct functions, means here it will be like, f1, okay, f2, f3, f4, and so on, and so on, f2 power k. Okay, so very simple. Now remember how we are getting these f1, f2, f3, and so on, f2 power k. Basically, these k don't care combinations, these can be, all zeros, these can be, like this, these can be, like this, and so on. Basically, you are getting the point. I hope you are getting the point. This can be like this. Okay, so very simple point. Now let me tell you that this function with don't care combinations, this is incompletely specified function, and because there are k don't care combinations, so I can say this corresponds to a set of 2 power k distinct functions. Now let me tell you that now few of these functions can give you minimal SOP for f. Remember, minimal SOP for a function may not be unique. So for this function f, if I find minimal SOP, then one or more minimal SOP are possible. So let's assume that this f1, f2, they are giving you minimal SOP, means this f1 is giving you, let's assume, minimal SOP 1 for f. Okay, and let's assume that this f2 is giving you minimal SOP 2 for f. So you can see f has two minimal SOP, and remember Minimal SOP may not be unique, but all the minimal SOP will have same number of terms, same number of literals. Okay, so it simply means that if F1, F2, if these are minimal SOP for F, then it simply means that they will have same number of terms, same number of literals. Very simple point. Okay, also it might be possible that a different function is giving you minimal POS for F. Okay, it might be possible that this F3 is giving you minimal POS for F, or maybe this F4 is giving you, minimal POS for F. So maybe this F4 is giving you minimal POS for F. So you can see that minimal SOP, minimal POS for a function which is incompletely specified, they may not be logically equivalent. Okay, if you have a function we don't care, then for that function, the minimal SOP and minimal POS, they may not be logically equivalent. They may or may not be. Okay. Also remember one thing, that the number of minimal SOP and the number of minimal POS, they have no relation. For example, for this function f, we don't cares. You can see we may have two minimal SOP, but there is only one minimal POS. Actually, this is true for all the functions, whether it is completely specified, fully specified, or incompletely specified. Means a function with don't cares or without don't cares. Remember, the number of minimal SOP and the number of minimal POS, they have no relation with each other. Okay, they may be equal, they may not be equal. One of them can be less, another can be less. Okay, so they have no relation with each other. So that is the reason in this photo everything I have covered. You can see here I have also covered this point, that the number of minimal SOP, the number of minimal POS, they may not be, they have no relationship with each other. They may or may not be equal. Okay, you can see. So that point also I have covered here, and you can see this point also I have covered, that for a function we don't cares, the minimal SOP, minimal POS may not be logically equivalent. Okay, let me just give you a quick example. Consider consider only two variables. Okay, so there are total four input combinations. Now let's consider a incompletely specified function. I'm giving you this incompletely specified function. Now you can see there are two don't cares. So this function, this is incompletely specified. You can see this function f, this is function with don't cares. We call it incompletely specified. Means this is not fully specified function. This is incompletely specified function. Okay, so this function has two don't cares, and these don't cares can be 0 or 1. So you can see each don't care has two possibilities. So I can say that this function f corresponds to four distinct functions. So you can see f1, f2, f3, f4. Here you can see the don't cares can be 0 0, they can be like 0 1, they can be 1 0, they can be 1 1. Of course the other values, of course, they will be as it is. You can see. Okay, now here you can easily notice one thing, that these are distinct functions. For example, if you write the expression for f1, then what expression you will get? 0 0 1 0. So this a b bar, this f1 is basically a b bar. Next you can see what is this f2. This f2 is same as a, so f2 is a. What is this f3? F3 is xor a xor b, correct? And what is f4? F4 is basically a or b. Yes or no? F4 is a or b. Okay, so very simple. You can see. Okay, so you can see this is ab bar, this is same as a, this is same as a xor b, this is same as a or b. This a xor b in terms of and or, I can write it a bar b or a b bar, like that I can write. Now you can easily notice that these are distinct functions. Okay, and here you can see f1, f2, f3, f4, which of them is giving minimal SOP for f, which of them is giving minimal POS for f? Tell me. You can see that this f2 is giving both minimal SOP for f and minimal POS for F. Okay, so this F2, this is basically this is basically minimal. This is minimal SOP for F also. This is minimal SOP for F also, and this is minimal POS for F also. Okay, so I told you that if you have a function with don't cares, then minimal SOP for F, minimal POS for F, they may be equivalent. Here you can see they are equivalent. Okay, the same function represents the minimal SOP for F. The same function represents the minimal SOP and minimal POS for F. Okay, but you can see in the previous example that we have taken, the variation of the MIT question that we have taken, there you can see that the minimal SOP, minimal POS for F, they are not equivalent. Okay, so this is the complete analysis of this question. I hope you understood. Okay, and you can read this comment by me. You can see on the Gate Overflow website under Gate CS 2003 question, you can see. So under this Gate CS 2003 question, this comment I have put here, and here I have written one thing, that for any Boolean function, whether it is completely specified or whether it is incompletely specified, means a function with don't cares or function without don't cares. Remember one thing, that minimal SOP may or may not be unique, but the point is all the minimal SOP, all the minimum SOP solutions must have same number of terms and same number of literals. Example also I have given, that if you have a minimal solution, minimal SOP with 3 terms and 7 literals, then no solution with 4 term will be minimum, and no solution with 3 term and 8 literals will be minimum. What I want to say, I just want to say that if you have any Boolean function F with don't cares or without don't cares, it can have many minimal SOP. Minimal SOP may or may not be unique, but all the minimal SOP will have same number of terms and same number of literals. Similarly, this function can have one or more minimal POS, but all the minimal POS will have same number of terms and same number of literals. And remember, the number of minimal SOP and the number of minimal POS, they have no relationship with each other. Okay, so very simple. That's it. This is the official answer given for the official MIT question. Okay, you know the MIT question that we have seen. You can see for that MIT question, the minimal SOP, minimal POS both are A or C, and yes, they were logically equivalent. So this is the official answer given by MIT for MIT question. But the Go classes variation that I showed you, that provides more knowledge, I can say. I hope you understood. I hope you learned something new. So let me see if there is any doubt in the live chat. So please tell me, please share your feedback right now in the live chat. Let me know. Was this session helpful? A student Karthik is asking, sir, these DPP available every day? Yes. So today is DPP 4. Please check out the playlist link. You can find the link of YouTube DPP playlist in the pinned comment, also in the descriptions. Masoom Mittal, excellent. Masoom is saying that he got to learn something new. Okay, excellent. So please share with me. Was this session helpful? I hope you learned something new. So remember, we have started Go classes YouTube DPP playlist, or I can say YouTube DPP series. In short, GOT DPP series. And your support will decide the future of this series. Okay, we will keep bringing you new unseen standard questions to solve. All these questions will be within the GATE CS syllabus, within the GATE CS level. All these questions will be taken from the standard resources. I will also mention from which standard resource I have taken these questions, so that you are very certain that you are solving the top quality questions. You are not solving, ill-framed questions. You are solving good quality questions from the standard resources. So that will give you some confidence, right? Okay. A student is asking, sir, will you do tabular method? I already mentioned about it in the day 1 DPP. Have you watched? I think this student has not watched the day 1 DPP solution. In that, actually, I've already mentioned about it. This in GATE 2027 computer science syllabus in the digital logic, they have mentioned tabular method. But let me tell you, this is not a new concept. It was already there in the GATE syllabus. In the GATE 2026 syllabus, They have just mentioned in the digital logic, just mentioned minimization. They did not mention K-map. They did not mention tabular method. In GATE 2027 computer science syllabus for digital logic, they have mentioned minimization, K-map, tabular method. Let me tell you that they have just explicitly mentioned the topic, but they did not change the syllabus of digital logic. One more important point. You might be thinking, sir, what is this tabular method? What are the concepts that we study in this tabular method? In the GATE exam, they can ask some question based on the concepts that we study in the tabular method. You might be thinking, yes or no? So let me tell you, in the tabular method, actually, we study prime implicant, essential prime implicant, implicant. These concepts, these are actually part of tabular method. Okay. So just I'm telling you that these concepts we already study without mentioning the name tabular method. These we have already studied. Implicant, prime implicant, essential prime implicant. If these three concepts you understand, then tabular method is over. Tabular method and K-map, these are two different methods. But remember, in the tabular method, the concepts that we study, these are implicant, prime implicant, essential prime implicant. Those we have studied. Okay, so I just want to tell you very clearly that there is no new addition in the syllabus for digital logic. Okay, so don't think that okay something new has been added. Please don't fall in these type of things. The people who tell you that okay, see, digital logic syllabus has changed, they actually don't even know. If you ask them what concepts come under the tabular method, they don't even know that prime implicant, implicant, essential prime implicant, these concepts we study in the tabular method. So these we have already studied. So don't worry. Okay, I hope it is clear. So thank you everyone. Please share the feedback, and in the comments after this session is over, please share your feedback in the comments. Did you enjoy this session? Did you learn something new in this session? Are these sessions helpful? And also, I request you that please share the word of Go Classes YouTube DPP series playlist. This YouTube DPP series that we've started. Please share the word with the Gate CS aspirants. Okay. If you use some social media, any social media platform, if you are using, then you can share a word. Okay. It will motivate me. I will see, and your post on any social media platform, you can just share with the Gate aspirants, with the Gate CS aspirants, and it will motivate me. I will keep bringing. And one more thing, if there is some holiday, let's assume I'm on off day, like for some work or for some family work, or basically I've taken some holiday, let's assume for 2 days, then also I will make sure that in those 2 days also I will pre-record the DPP. But from my side, I will make sure, I will try my best that every day you get 5 standard questions to solve, at least 5 standard questions to solve. Maybe in the future we can increase the frequency, and we will do the subjects in the round robin fashion. So you can see, so far digital logic we have covered. Okay, and then we will take some other subject, then we will take some other subject in round robin fashion. We will continue the subjects. Okay, so thank you everyone. Please share the word of Go Classes YouTube DPP series with the Gate CS aspirants. Okay, thank you. And please share your feedback in the comments. Thank you.